Greetings all and welcome to a new video about another control system topics. We continue with the drawing of the Bode plot from a transfer function, and this will be our example number 2. So we will move on with this topic. Of course, we will work out the calculations step by step and then verify these in simulations using MATLAB. So let's look at this example. We have the following transfer function. This is our system. It's also called the plant. And we would like to draw the Bode plot of this. Now, let's work out the solutions. First step, as we did in the previous example, we rewrite each term normalized to a low frequency gain of a unity. But before we move on, let's first recognize several things here, because this is a third order system which has a real 0, 1, 0, one real pole, but it has also a second order term here which must be, let's say, dealt with in a different way. But we know this can be rewritten in the standard form, which is then s squared plus 2 zeta omega ns plus omega n squared. Omega n is here the natural frequency or undamped radiant frequency. The zeta is here the damping ratio. So we can now recognize and compare the terms. So we have 2 times zeta times omega n is 2, and then omega n squared is 25. So that means omega n itself is then the square root of the 25. So we can move on or write that in a different form, which is then useful for our drawings for the Bode plot. And then we can also recognize that this can be transformed in that fashion by dividing each term by 25. Okay. So what we have then next, how we continue. Okay, now we can say first the radian frequency is again 5 radians per second, so the undamped radian frequency. And a zeta can be then determined by comparing this term and equating that to 2. That's actually what's shown here, and that is then the zeta, and it will be then 0.2 or 1 over 5. Okay, now that part is done, so we know the second order term, which are the complex pair of poles. So we can then rewrite this as such. So we have then 800, and then we remove the 0.5 out of it. So we have then a low frequency gain and a unity. So low frequency and then a unity. And we have also the 9 out of it for the real pole, and also the 25 out of this term. And you can see and recognize also the 0.2 for the damping ratio and also the 5 for the natural frequency. Now let's then simplify this, because 800 times 0.5 is 400, and this times that, so 9 times 25 is then 225, etc. Then we can of course also divide the 400 by 225, and then you will get 16 over 9 as an exact value. The rest are exact same as before. Now, then we have this expression, which is then what we will use for our drawing. So the second step is determine the DC gain and also the break frequencies. DC gain is, as we have discussed earlier, is the gain of this system where the omega is then set to 0, so or the s is equal to 0. So you can see here, recognize that much faster. So if you have an s is equal to 0 here, that goes, so you only leave 1. This goes, and this goes away, and you also lose this, so you actually have 1 times 1 in the denominator, and then 1 times the 16 over 9, which is then just 16. So the DC gain K is then 16 over 9. We have to, of course, convert that in dBs using this formula, because we need to draw the magnitude plot, and then we have dBs as a unit. So this will be then approximately 5, so very close to 5 dBs. Okay, the break frequency, as we said, we have real 0, 1, 0, so 0.5 radians per second. And we have one pole as a real, which is then 9 radians per second, and we have complex poles, which are in pair, of course, and we have then the omega of natural frequency of 5 radians per second and associated damping ratio. Okay, now the magnitude plot, for that we need to determine the lowest and the highest frequency for our drawing. So for the frequency axis and the horizontal axis, it begins at least 1 decade before the lowest break frequency, and extend at least 1 decade above the highest break frequency. In this case, this is the lowest, 0.5, and it is the highest, which is then the 9. So we will extend in this format. So we will go from 0.05, so 10 times smaller, that means a decade. And we go up to 90, so it is then at least, of course, then it is then 90, it's 10 times larger. Of course, you can do more, so you can also start at 0.01 and up to 100 or 1000, but it is at least what you need to have in order to make that drawing more exact. Okay, now let's then move on and then to the step 3, which is then the slope for the magnitudes. That means how much contribution I will get for each pole and each zero for my magnitude plot. Now we have seen this before. We start 1 decade below, so that is actually our starting point. This is the starting of the first, the zero, the real zero. This is the starting of the let's say the undamped frequency part, and this is the real pole. So we have also a description here, and in order from 0.5, 5, and 9, so from lowest to highest frequency. So the first part, this, of course, first the DC gain. First part, this one, will have a slope starting actually here. So it was 0 dBs per decade, but it will then have a 20 plus 20 dB per decade, and it will have that slope. So for each zero, you will have, for one first order real zero, you will have plus 20 dBs per decade. If you have, for example, a second order real zero, that will be then plus 40 dBs per decade. Now for this is then a natural frequency part, so it's actually a peaking part that will start at 5 radians per second, will then go down in a second order fashion, because it is a pole, complex pole, it will have a negative, it will be minus 40 dBs per decade, and it will then keep going. Of course, for higher frequencies, this is the same slope also for the zero. Now for the pole, it starts actually here, because it is all 0 dBs per decade, but it will then decrease as a first order pole as minus 20 dBs per decade. Now in total, you will have on total slopes, you will add all these numbers. So for each column, you will get 0, 20 dBs per decade, etc. Okay, now we need to draw these elements and then make up the complete magnitude plot. So let's bring up the plot. So this is then just an empty plot. So we will now draw the segments here. The first, we will recognize again the break frequencies. 0.5 for our real pole at 9 radians per second. And we have also that natural frequency at 5 radians per second. Now we know it started with a slope of 0 dBs per decade, but we need to also check that DC gain. So we start at the height of 5 dB. So if I just make this a little bit accurate, and then also place here a 5, which is then actually our 5, and this has a slope of 0 dBs per decade. So this is 5. It starts at, so let's say, low frequency. I have now 0.01 chosen, but you can of course go lower, and then up to the first break frequency, which is then our 0.5. Your slope will be 0 dBs per decade. This is an asymptotic approximation, of course. Now the next slope is then 20 dBs per decade, so that will go up. Of course, I have to check also how much I go up, because for example, from 0.5 up to 5, which is actually 1 decade above, so you do 10 times, your slope is 20 dBs per decade. So that will go up in this fashion, and you will now have, you will increase from 5 to 25. That is actually an increase of 20. That's exactly this slope. So it is exactly coming here nicely. Then we have the next one, which is then minus 20 dBs per decade. So we need to also draw that. So from 5, for example, to another value, first recognize this. Now let me just also designate this value, which will be handy for our drawing. So from 5 to 50 is again 1 decade above. So I will then decrease by, again, 20 dBs per decade because of that. So I will then decrease that value. But I have to go, of course, from 5 to 9, not from 5 to 50. So I can then say this is indeed 20 dBs per decade, but I have to actually go up to here. So let me go back, and then this is of course how we do, but you need to stop actually here. So you can see it is actually stopping there, and then it will reach another slope, which is the minus 40 dBs per decade from 9 to higher frequencies, and that is actually the next part. So it will then, going from, let's say, 9 9 to 90. Again, that 90 is 10 times larger, and it will help us to draw that slope. First, we just draw that slope, and then recognize that we need to move on with that slope, and then that is our minus 40 dBs per decade. Okay, then that is then the total plot. So we have for each section the magnitude plot given. Of course, we need to check this later, and we need to make, if necessary, some corrections on it, because we have some complex poles. Okay, all right. Now let's then look at the correction, because since this pole, since this omega n is due to that complex pole, so we need to also look to that more carefully. This is a plot which actually plots normalized normalized natural frequency as a function of the zeta, which is then our damping ratio. So you can see for higher damping ratios there are no peakings, but if the zeta is going lower, for example to 0.3 or 0.2, which we had in 0.1, the peaking is quite high, and then we need to, of course, correct this asymptotic approximation, because that will not be valid anymore. So you will see more differences between the actual and the asymptotic approximation. And this is a table. You can see in this table the following. This is omega over omega n. So it is actually sort of a normalized frequency. And this is the column where we are interested in, because the magnitude and also the phase. So this part, we have for undamped second order term, we have complex pair of poles, of course, and it will have a correction for the natural frequency by taking the values from the curve or from the table, depending on what you prefer. This is sometimes much easier. And how to do the correction? Now, the plotting using the correction is this value, so you will actually use this value for the correction you require. So in our case, the damping ratio was 0.2. That is our second order term, and in the denominator of that plant. So if I now work out the correction, so it is minus 20 log 2 times our damping ratio, which is 0.2, I will get approximately 7.96, let's say 8 dBs. That's actually also shown here. So let me zoom in this part, because this is the highest value, so let's say 25, and I have to actually go up to and make a correction of 7.96 dBs, which goes then to 32.96 dBs. Now you can see that in the table also. So I have now made this clear, this column, and you can see in this part, which is then 1, which is then a normalized frequency. So you look at omega over omega n, and then you just substitute your own omega, that will be then 5 over 5. And you will see here how much gain peaking you will have. That's also for the phase. You can see how much phase you will then have. If you, for example, look for other break frequencies, let's start, for example, with that 0.1, which is then the 0.5 over 5. And you will see this much correction I have to make, 0.08, which is not that much, but that is the correction I have to add. And for the other one, which is then 1.4, because 9 over the 5, which is then 1.8 actually, so that's actually this one, that will be then 7.43. And this is for another one. So that is actually, you can just move on and then work out this for other values. Okay, so we need to make some correction, but it will be discussed in great detail when we see this simulations also. Now, let's then move on to step 4, which is, of course, looking again at the slope of the faces, and then contribution for each pole in 0. Again, the description, the 0, the natural radian frequency, and our pole. So we have 2 real pole in zeros, and we have 1 natural frequency due to that complex pair of poles. Now we need more bookkeeping in this phase slopes. We start always 1 decade below, and we end at the 1 decade above for each break frequency. So for that, we start at 0.05, but we stop at 5. So that's actually the starting of the 0.1 and the ending of 0.1. So you actually set that in order. It's also for this, so 0.5, it starts, but it stops at 50. So you can see. And you start at 0.9 and you stop at 90. So you will actually have 2 columns for each break frequency. So that's actually 1, 2, 3, 4, 5, 6. So how do we then move on? Now the increase, the slope for the phase contribution by one real zero is plus 45 degrees per decade. That will go on. First it starts one decade before, so below this value, and it will reach actually that up to one decade above. So it's actually having the same slope up to the one decade above. That is the approximation using asymptotic lines. And then it will keep, of course, 0. Now for the second order term here, it will have a minus 90 degrees. So because of its second order pole, it is minus. That's because of the pole. It starts here, keeps that value, the slope, and keeps that value still. And at 50, it will then have 0, and it keeps that 0. For the real pole, it starts at 0.9, of course, with a minus 45 degrees. It is negative again, but it's the first order. It is a pole. It keeps that slope and then ends at 90. Okay, so how do we then move on? Now, we just add all these slopes. So we get plus 45, minus 45, plus 90, minus 135, minus 45, and then 0 degrees. So you can actually see for each segment what the slope is. Now, let's bring up the plot. This is our Bode diagram, but specifically for the phase. And again, let's recognize the poles and the zeros and also the natural radian frequency. Now, since we know that we need to start at 0.05, let's also denote that clearly. And we know that we have then a phase of, the slope of 0 degrees per decade up to that. It's starting then from here and keeps decreasing. So this is actually just looking at the 0. So it will then increase from 0.05 up to 0.5 by 45 degrees per decade, or 90 degrees per 2 decades. So it's going from 0.05 to 0.5 to 5. So this is actually 1 decade, 2 decades. So you increase from 0 to 90. You can see that. And then it needs to have a slope of 0 degrees per decade. So this is just, that blue line is just considering only the 0, 1. Now let's also focus on, this is the 0. Now let's also focus on that omega n. So it will then start at 0.5. So from there, before that it was just 0. And then it will decrease by minus 90 degrees per decade. Now I have to go from 0.5 to 5 and up to 50 for the drawing. So going 1 decade, so it's actually this, you can see 0.5 to 5 is 1 decade above. So I will decrease from 0 degrees to minus 90. You can see this is just 1 decade above in the frequency. I will go down by 90 degrees, which is according to this. And you will keep that slope. So again, from 5 to 50, you will go from minus 90 to minus 180. And then from 50, I have to have a slope of 0. So you can see it will now have a horizontal line. Okay, then this is then for the complex poles. Now, the final one is the real pole. It's starting at 0.9, so let's also recognize that here. That's the dotted line, the red one. And now it starts there, and I will also go from 0.9 to 9 or 90 to make it a little bit more clear. So how much I have to go? Now it is then minus 45 degrees. You can see it started at 0.9 going to 9. So I have then decreased in 1 decade my phase from 0 to minus 45 degrees. Again, the same slope, and the same for the next decade also. Now and then it has a slope of 0 because it has then after 9 radians per second a slope of 0 degrees per decade. Now the total effect, these are all parts of the complete plot. Now I have to make the complete plot out of this. So this is then for the pole. So then look at the complete plot. This is then again the segments 0, the pole, and the complex pole pairs. Now let's then make the complete drawing. We recognize all of our poles and the zeros and the natural radian frequencies. Okay, now how do we start? Again, we start with a slope of 0. Then you can see the total effect is by adding each slope together. So from this to that point, only the blue line is doing some work. So it goes to plus 45 degrees per decade. Then you can see this will increase, the blue line. This will stay the same, so it doesn't add any slope. But this will go down by minus 90, so this part from there to there, so from 0.5 to 0.9, you will have a slope of plus 45 degrees per decade plus minus 90 degrees per decade will be the minus 45 degrees. So if I now draw from 0.5 up to 5, that line, that is actually a decrease of 45 degrees per decade, then I have to stop at 0.9, so I have to go back, and this is then the line. Okay, and this slope is then minus 45 degrees per decade. Now I have to go from the 0.9 because then I have again a change because this red line is now coming up, and that will of course cancel this blue line completely, and I have only minus 9 degrees per decade. So this slope will be then twice as steep down. You can see from 0.9 to 9, that is 1 decade above again. And I see I have to stop at 5 actually because something is again changing, because the 0 will be then, will not contribute any slope. So I have to stop actually here. So this is actually just a drawing to make sure how you need to set that slope. And then you can then remove that and then stop there. And this part from 0.9 to up to 5 is the slope of minus 90 degrees per decade. Now from there, actually, I have now this slope, minus 45 degrees per decade, and I have this slope, which is the minus 90 degrees per decade, in total minus 135. So that's actually this. So again, we use the, let's say, the handy way from 5 to 50, so 1 decade above. I have to go down by minus 135 degrees. So this is approximately, let's say, minus 40, and I have to go up to almost a little bit higher to that. So it is, this decrease is minus 135 degrees, approximately. Now, then I know I have to again make the change, not at 50, but at 90. So this is actually how far I have to go. And I also, excuse me, we need to make a change at 50, I mean, because then this pink line will not contribute any more slope. The only slope we will have is that minus 45 degrees. So from there, I have then again a line up to 90, and that will have minus 45 degrees. And then it will have a slope of 0 because all of the elements have a slope of 0 degrees per decade, and that will then have this one. So you can see in this plot that is actually going from 0 degrees to up to 45 plus 45 degrees, and then going down and up to actually a little bit more negative than 108 degrees. It sounds actually maybe strange because we have a second order system. How can we have more negative than 108 degrees? That's because of that peaking, so we have some extra phase here, and it will also go down a little bit lower there than actually it is drawing here. That is due to that asymptotic approximation, so we need to also correct for this. But we'll see that when we have that simulation. But this is the total plot using just asymptotic approximation, and it will be then very close to what the actual value will be. Okay, now let's then look at the simulation result and then discuss this in more detail. Now, first the comparison. This is the complete plot. Is just the poles, I mean the magnitude and the poles, the phases of the system. You can see it is starting at 5 dBs and increases. It is here not 8, so it's actually at the first break frequency it had to be the 8, so it is 3 dBs up for 0, but it's 8.08. And if you remember from the table for the correction for the second order system, we need to have actually here a 0.08 dBs addition, and that is exactly the correction we need to make, and then we come up to the right value. So for each break frequency, you know for sure, for the first order zeros, we have 3 dBs up, and for the first order poles, you go 3 dBs down. And again, due to that peaking, you will also have 0.08 dBs correction. Now, we can see that in great detail when we compare the magnitudes and the phases with our drawing. So this is just the magnitude plot in the simulation in MATLAB, and this is our drawing using asymptotic approximation. You can see we are at 25 dBs here for the peaking, but that goes to almost to 31.8 dBs. So that is in our approximation, and then also using the correction goes to 32.96, and that is the correction we need to make, but I see it is 31.8. So why is that not exactly as here? That's due to that pole at 9 radians per second, which is close to that 5. So it is at 5 approximately, which is then our natural radian frequency. It is then sort of decreasing this peaking more because it is then closer. If this is, for example, at 90 or 900, this will be much, not much, but a little bit higher, and it will be then exactly at this value as we have calculated using that correction. So that pole will have an effect. Now, also looking at this, so that it has some difference, let's say 1 dB difference between the simulation and also the calculation using correction. You can also see the DC gain at 5 dBs, and it's also 5 dBs here. Okay, and it goes also, if you look at this one, if you look at 25 radians per second, it is then 1.94 dBs, but if you go to 50, so it is then twice the frequency. So that means you double the frequency, that means 1 octave above, and you will go down actually 12 dB. So 6 dBs per decade per order, and it's then 2 times 6 dBs per decade actually for second order. So we have now 12 dBs per octave for the second order pole. Now, that's also true here, and we can see that this is exactly in agreement. Okay, now we also look at the Bode diagram for our phase. Again, it starts at 0, so it's close to 0. Of course, if you go to low frequency, this is very close to 0. It's just an approximation, of course, here for our case. And the first break frequency 0.5, we had calculated using asymptotic approximation. It was 0.45 degrees, but it is approximately here 40. So you can see again some difference. You can also see that it goes higher than 45 degrees, which is not the case in our case, because we are saying that already this is decreasing here, which is not the case there. So that is due to that peaking we have, and that peaking will add some correction. And that is then here what you actually need to add using that table. Now we also move on to the other, for example, the 5 radians per second, which is our natural frequency. You can see it is at approximately minus 35, approximately, and we have also approximately that. So maybe minus 40, minus 38, but it's close. But then the situation will be changed because this goes much faster, and then the slope decreases actually also quite drastically, because this one has a slope of minus 135 degrees per decade, and this slope will then decrease not as fast as in this case. But then it will approach asymptotically the minus 180 degrees, which is not in our case. And again, if you lift this green asymptotic line up, you will get the closer value we need to have according to the actual plot. So you can see the phase plot, what we have drawing using asymptotic lines, and the phase from the Bode diagram using the simulation, the actual plot, is quite similar, using of course some correction, because you need to go up here, and then this will also go up, and then you will have more correct values. And that is actually the situation here, because if you look at 9 radians per second, it has minus 120 degrees. If I look at this, it will have approximately maybe minus 70 degrees. So that is really the situation here, that this is decreasing much faster, and due to that asymptotic approximation, we don't have the, let's say, the continuous curvy lines. But it will give you an idea if you just place this green line on top of this actual line. You can see it is looking very close to that line if you just compare the shape of it. And that is actually also what the purpose is of our drawing, because we can never make it exactly, because it has, we also approximate this by some segments, so we will have some limited accuracy. But at least we can move on and then decide for ourselves how we approach the phases for specific frequencies. All right, this is then for this example about a third order system having a real pole, one real zero, and a second order complex pole pairs. And we have also seen how we do the correction in the magnitude plot. If you have any questions,